Welcome to AGRON Info Tech. In this video, we build the foundation of tidy machine learning with nested data. The main idea is very powerful. Instead of keeping data in one place and models in another place, we organize everything inside a tidy workflow so the analysis stays clean, readable, and easy to scale. First, I load the required packages. I use Tidyverse for data manipulation and plotting, Gapminder for the public data set, and Broom for turning model output into tidy tables. Each package has a clear purpose here. Tidyverse helps with wrangling and list columns. Gapminder gives us a compact country-by-year dataset, and Broom makes model summaries much easier to read and compare. Now I load and tidy the dataset. Here I use transmute because I want to do two things at once. I want to keep only the variables that matter for this lesson, and I also want to rename some of them into clearer teaching-friendly names. So I keep country, continent, and year, and then I rename life expectancy, population, and GDP per capita. This makes the script cleaner and makes the narration sound more natural than reading the original variable names directly. When I print the first few rows, I get a 6-column tibble. The first 6 rows all belong to Afghanistan because the dataset starts there. We can already see a time series pattern. Life expectancy moves from about 28.8 to 38.4 in those early rows, while population also rises across the years shown. Then I use Glimpse to inspect the full structure. The output tells me the dataset has 1,704 rows and 6 columns. Country and continent are factors. Year and population are integers, and life expectancy and GDP per capita are numeric. This confirms that the data is tidy and ready for the next step. Now we move into the core idea of the video. I group the table by country and continent, and then I apply nest. I specify country and continent inside group_by because I want those two variables to stay outside the nested cells as identifiers. Then nest takes all the remaining columns and stores them inside a list column called data. When I print the result, the structure changes in a very important way. Instead of many rows per country, I now get 1 row per country and continent plus 1 list column. In the output, each entry in that data column is a tibble with 12 rows and 4 columns. That means each country now carries its own full mini dataset inside a single cell. To make that more concrete, I inspect the first nested tibble directly. The output shows Afghanistan's 12 observations, with year, life expectancy, population, and GDP per capita stored inside that one nested object. This is the moment where nested data becomes easy to understand. 1 row in the outer table now holds an entire country-level time series. Next, I unnest the data to confirm that nesting only reorganizes the structure and does not change the values. Here, I specify the data column inside unnest because that is the list column I want to expand back into ordinary rows. Then I compare the original table and the unnest table after arranging both by country, continent, and year. The output returns true. It confirms that the nested and unnest versions contain exactly the same information. The only thing that changes is the shape of the table. Now I focus on one nested cell, so the workflow feels more real. I filter for Algeria, then I pull the data column, and finally I extract the first element from that list. I use filter because I want only one country. I use pull because I need the list column itself. Then I extract the first item because there's only one nested tibble left after filtering Algeria. Once I do that, Algeria's time series becomes an ordinary tibble again. I calculate the minimum, maximum, and mean population. The outputs show that Algeria's population goes from 9,279,525 at the low end to 33,333,216 at the high end, with an average of 19,875,406. This is a nice example of how we can move from a nested structure back into familiar summaries whenever we need to. After that, I use map functions to calculate summaries for every country at once. Here I choose map_dbl because each summary returns one numeric value, and map_dbl gives me a clean numeric column back. I calculate mean population, minimum life expectancy, and maximum life expectancy for each nested tibble. When I print the result, I now see a richer tibble with 3 new summary columns. For example, Afghanistan has an average population of about 15.8 million, while Algeria has an average population of about 19.9 million. Algeria's minimum life expectancy is 43.1 years, and its maximum is 72.3 years. This shows how list columns and mapping functions work together to scale the same operation across many groups. Now we build one linear model per country. This is the first real modeling step of the lesson. Inside Mutate, I use map again, but this time each nested tibble is passed into a linear regression. The formula uses life expectancy as the response and year as the predictor because I want to measure the long-term trend in life expectancy over time for each country. I also specify the data argument, so the model knows to use each nested tibble separately. The output is another tidy table, now with a new list column that stores one model object for every country. To understand the model clearly, I extract Algeria's model and print the summary. The results are very strong. The coefficient for year is about 0.569. This means that, according to the fitted line, Algeria's life expectancy increases by roughly 0.57 years for each 1-year increase in time. Since the dataset moves in 5-year steps, that is about 2.85 years of life expectancy gain every 5 years on average. The p-value for the year coefficient is extremely small, which tells us that this upward trend is statistically very strong. The R-squared is 0.9851, and the adjusted R-squared is 0.9836. That means the model explains about 98.5% of the variation in Algeria's life expectancy across these years. The residual standard error is about 1.323, so the fitted values stay quite close to the actual values. The intercept is a large negative number, but that is not the main piece to interpret because year 0 is far outside the real data range. The key message is the slope, and the slope is clearly positive. Now, I tidy the model outputs with Broom. First, I use tidy, which gives 1 row per coefficient. This output includes the term name, the estimate, the standard error, the test statistic, and the p-value. For Algeria, the year coefficient remains 0.569 with a standard error of about 0.0221 and a very large test statistic. This confirms that the time effect is both strong and precise. Then I use glance, which gives me 1 compact row of model-level statistics. Here I can quickly see the R-squared, adjusted R-squared, sigma, F-statistic, p-value, AIC, beach C, and number of observations. The glance table confirms the same strong fit in a very concise format. This is one of the big strengths of tidy modeling. Model results become regular tibbles that are easy to compare later. Next, I augment the Algeria model. This step adds fitted values and diagnostic information back to row-level data. That is why augment is so useful. It reconnects the model output to the original observations. In the first few rows, I can compare actual life expectancy with the fitted values directly. For the first observation, the actual value is 43.1 and the fitted value is 43.4. So the residual is only about negative 0.298. In the second row, the actual value is 45.7 and the fitted value is 46.2. So the residual is about negative 0.536. In the third row, the actual value is 48.3 and the fitted value is 49.1. So the residual is about negative 0.765. These are all fairly small differences, which already suggest that the line is following the data closely. Finally, I create a plot of actual versus fitted life expectancy for Algeria. I map year to the horizontal axis because time is the explanatory variable in this model. Then I add black points for the actual life expectancy values and a red line for the fitted values. I set the point size to make the observations clearly visible, and I set the line width to make the fitted trend stand out. I also add a clear title and axis labels so the chart is easy to understand at a glance. and I use a black and white theme for a clean teaching style appearance. When the chart appears, the story becomes very clear visually. The black points rise steadily from the early 1950s to 2007, showing that Algeria's life expectancy improves strongly over time. The red fitted line passes very close to those points across the whole period. In the middle and later years, a few points sit slightly above or below the line, but the departures are small. That visual pattern matches the numerical results we already saw in the model summary. The high R-squared and the small residual spread makes sense because the line tracks the data so closely. So in this lesson, we move through the complete tidy machine learning foundation. We start with a regular tidy table, convert it into a nested structure, verify that nesting preserves the data, explore one nested country, compute map summaries across all countries, fit one linear model per country, and then turn the model results back into tidy outputs and a clear visual. This is the basic pattern that makes more advanced tidy machine learning workflows possible. In the next video, we build directly on this foundation and compare coefficients across many country models so we can move from one example to a broader cross-country story.